Alright guys, welcome to our channel Code with Sunny, and in this video I will be again talking about lead code problem, the medium type problem, number of subarrays with bounded maximum you can see. Okay, and its index is 795 and it is categorized as the medium type problem of the lead code. Right, so before moving further to discuss this problem, I just want you guys to vote up on this poll that I've created over here. Like I just want to know which is in high demand being required by our viewers, and you just have to do one thing: visit my channel and just vote up your best like that you want among these 4 or 5 options that are present over here, right? So okay, so moving further to discuss this problem, so we have been given an array nums of positive integers, and two positive integers are also given to us, left as well as right, and left must be less than or equal to right. So return the number of contiguous non-empty subarrays. Note that the subarray must be non-empty, and as it is a subarray, it must be contiguous, right? Such that the value of the maximum array element in that subarray is at least left and at most right. Okay, so you need to find out what are the total number of possible subarrays from the given array that can be built up, that can be extracted, such that if we try to find out the maximum array element in that subarray that we have chosen now, then that value is at most right and at least left. I guess you guys have understood that problem. Now moving further to the example, and we will together build up the solution for this problem. Right? If you still haven't understood the problem yet, no need to worry about. I'm going to explain this problem in the little bit detail with the help of explanation, and then we will together build up the best solution for this problem. Right? Many people have solved this problem with the help of stack. We can solve this. We can find out the total number of subarrays, right? But what I have done in this like the solution for this problem is like I've used the binary search technique, right? So I'm going to discuss that in a little bit detail now. For one thing that should be noted over here is like the constraints. You can see the length of nums will be in the range of 1 to 5 into what is this value, like 4 times 0, so 5 into 10 power 4. We can have a like O of n log n solution. Okay, and we will try to like improve my solution, but I don't think like using like a stack technique is like better, but we can use that. But the to understand this problem in a detailed manner, you need to have the concept of binary search. What is happening over here with the help of like binary search, we can easily understand that, right? So let's move further to understand this problem with the help of example, and then we will together find out the best solution for this problem, right? So let's move further. Okay, so here you can see I have taken one example, and left is 3 and right is 8. Okay, now if we have been asked to find out total number of subarrays such that the maximum element in that particular subarray is at least 3 and at most right. Okay, so let's try to pick up one subarray. Like okay, so I am going to try to pick up one subarray like this one. Okay, so if whether this is a valid subarray or not. Let Okay, so let me try to pick up another subarray like this one. Okay, suppose I have chosen this subarray. What is the maximum element in this subarray? You can see the maximum element is coming out to be 5. Okay, and what is the minimum element? It doesn't matter what is the minimum element. We need to focus on the maximum element, right? So 5 is at most right. I think right is what? The value is like 8, and it is like greater than or equal to 3. Okay, so this is the valid subarray. Okay, so we need to find such valid subarrays. Okay, so we need to find such valid subarrays, and we need to basically report total number of valid subarrays such that the maximum element present in that subarray is at least 3 and at most 8. How we can start thinking upon this idea? How we can approach the answer? This is going to be like really very much important. Okay, now if you have been watching my videos regularly, you can easily understand the what is the approach that I am going to use. Okay, you can easily see whenever there are some conditions like left is going to be like less than right, or some condition, two or more conditions, like one or more conditions. If I have been memorizing that problem, okay, so maximum performance of a team, yes, right. Okay, so if you focus on this problem and if you have watched my video, what I have been said that like we have been given two parameters, speed and efficiency, and we need to find the maximum performance and multiplied by the minimum efficiency and the sum of the speeds. What I've done is like I've fixed one condition, like we need to work upon two conditions. Sum of the engineered speed should be multiplied by the minimum efficiency. So what I've done in this problem is like I fixed this minimum efficiency because there are two conditions. We are not going to simultaneously work upon these two conditions at a time. So I have fixed one condition. The exact same thing is going to happen over here. Like what I'm going to do, I'm going to fix this maximum array element. Okay, so what does this help us? Like fixing or let's say claiming some element, or let's say saying some element as the maximum element, then how we can find out the number of subarrays corresponding to that maximum element. Okay, so if you're not going to understand this, no need to worry about. Let us understand this problem in a much more simpler way. And what is that simpler way? Okay, so let's say that this is a maximum element, and we don't know the left bound of the subarray that I have chosen. That is the subarray that I have chosen. We don't know the left bound and we don't know the right bound. Maximum element of some subarray we don't know. Okay, so I am going to fix this. That is, you can easily understand that what is my idea, that you can also think start thinking like that. Like I am going to fix every element and let's claim this as the maximum element. Like if you recall this statement in your mind that let's say array of I is the maximum element, then what are the number of subarrays that I can choose, right? Okay, so no need to worry about if you're not going to, if you're not grasping this logic. Let me explain in a much more easier way. Okay, so let's say this is the maximum element, and if you want total number of subarrays such that this element remains the maximum element, you can see if you try. Okay, so L is the left bound of this subarray and R is the right bound of this subarray, and there is an element 5 which exists in that subarray, right? Initially L is pointing to, let's say I'm going to mark this indices like 0 base 0 1 2 3 4 5 6 and 7. Right, initially L is marking as 3 and R is marking as again 3. Now initially I have chosen the maximum element as array of 3 and it is the value 5, and L is 3 and R is 3. Now my subarray is of length exactly equal to 1, whose left bound and right bound is going to coincide. You can easily see that if I will try to extend this right bound R to some greater index, like if you try to extend this R to 4, still my maximum element remains as 5, right? And if you try to extend this R to up to 3, that is R becomes as 5 and L is still 3. You can easily see my array is my array becomes 543. Sorry, subarray becomes 543, and still my maximum element remains as 5, right? And that's if you start thinking upon like that, what I'm being doing here is like I'm extending the right bound of this subarray such that the maximum element remains same. This is going to be like very much important. So I can extend up to 3, and if I will try to extend up to 8, you can easily say no, I cannot extend up to 8 because the maximum element changes, right? Because 8 is greater than 5. So it means that what is the maximum right bound of the my current subarray where I can extend that is my current chosen subarray. You can see I can extend up to 3. Okay, and what about the left one? Can I extend it to some minimum index? Yes, I can extend it. I can extend up to 2. You can easily see from this one, that is up to this 2, up to the index inclusive. I'm talking about index equal to 1 inclusive. I can extend my left bound up to this index equal to 1. Okay, so my subarray can vary from, okay, so I'm going to write below one thing. My L can vary from index equal to 1 up to index equal to 3. Right, and what is the my right bound going to vary for my current maximum element? It is going to vary from 3 up to what is the maximum right index? You can see 5, right? Okay. Okay, so my left bound can vary up to this one and my right bound can vary up to this one. Okay, so if you need to find out the total number of subarrays, what is the number of elements, number of indices present in this one? You can see there are three different indices, and in this one there are three different indices, right? 2 3, that is L belongs to 1 2 3, and R belongs to 3 4 5. Three different indices for this one and three different indices for this one. So my answer as total number of subarrays for my current maximum element array of I equal to 5 is going to be incremented by answer equals answer plus, okay, and this is the, let's say the total number of values for this one is as left. Okay, so not calling as left, I'm trying to call it as backward, and let's call it as forward. So my answer is going to be incremented by backward into forward. Why into? That is why there is a multiplication sign. The reason is quite simple. There are total backward amount of left bounds you can choose for my current element to remain as maximum, and there are forward amount of right bounds you can choose, so such that the maximum element remains same for my current chosen subarray. So there are total backward into forward amount of subarrays we can choose for my current element to remain as maximum. Okay, so what is my total answer? My total answer would be like, okay, so I'm going to write it out. Total answer is going to be summation I equal to 1 up to I equal to n of, let's say, backward of I into forward of I. This is my answer, right? So summation backward of I into forward of I. What is backward of I? Backward of I is the, what is the least index such that my maximum element array of I remains as maximum. Okay, and not the least index, it is the count. Sorry for speaking some wrong words. This is actually the count. You can see backward of this one is actually the value count, and it is actually the number of elements in this range, and forward is actually the count in number of elements present in this range. So backward of I and forward of I are the respective values where the maximum element remains as maximum. What is the least, that is we can minimize this L, that is the left bound, such that the maximum element remains as maximum. Also we can maximize this right bound such that the maximum element remains as maximum. And backward of I and forward of I is basically, you can easily say I minus L minimum. You can easily say backward of I, that is I is current index minus L minimum, and forward of I is like R maximum minus current index. And we need to find the summation for every element. Why for every element? We are trying to just fix it out, that we are trying to just claim that current element is the maximum element, and how we can fetch the answer by considering this as the maximum element. Okay, so how we can implement this in the coding part? Let us try to understand this in simpler words. Let's move further. All right. So in the previous one, you have seen that this is actually the array, and if we sort the elements of this array on the basis of a pair, and what is that pair? I am going to sort the elements on the basis of nums of I, comma the index. Why I'm going to sort this on the basis of this? Okay, as I've already said, that if you try to fix one of the element that is claiming that it is a maximum element, the main thing that is going to vary upon is like what is the minimum index, that is you need to find the next greater element and next smaller element, right? That is, if you focus on the previous thing, that if you're trying to claim that 5 is the maximum element, the next greater element's index is 8, and the next greater element to the left of 5 is 9. Okay, you need to find the number of elements present in this range, right? If you try to focus one thing, that both 9 and 8 is greater than 5, right, it signifies that you need to process the elements from the backward side. Okay, and how it is going to help us? Let us try to understand that. It is going to help us if we try to sort the elements on the basis of nums of I and I, then we will try to process the indexes. Note that I'm talking about index. Okay, so if we try to process the array of vector pairs from the backward side, and I'm going to talk about the index. I will stored index in stored index in a set. How this is going to help us? Okay, no need to worry about this, is going to help us, and the reason is quite simple. Okay, so let us try to understand one thing also. Like if we move on to this one, let's say I'm talking about this element 4. Okay, so this element 4. Okay, so this is actually being rubbish. So this element 4, right? So what is the fourth next greater element to the right of it? You can see fourth next greater element to the right of is 8. Okay, and what is the 8 index? 8 index is coming out to be 6. Okay, and what is the fourth next greater element to the left of it? It is coming out to be 5, and its index is 3. Okay, and let's see how it is going to help us. Okay, so I think I've missed some 2 3 3 4 8 9 9. Okay, 2 3 3 4 8 9 9. 3 elements, 6 and 2 8 elements. 3 elements, 3 elements. I think I've missed one element. Okay, so I'm going to write as 5. 5 as okay, what is the index of this 5? Index of this 5 is coming out to be 3. Okay, so what I'm going to do is I'm going to process the indexes from the backward side. Okay, and let's say we are at an index, and what is that index of 4? Index of 4 is coming out to be 4. Okay, so index of 4 is coming out to be 4, and okay, so when we are at this index, right, when we are at index equal to 4, we can easily answer if we store the values of indexes in a set like 43607. Okay, so let us store the values of indexes in a set, and so set will store the values in non-decreasing order right now. So 0 3 4 6 7. Okay, and let's say we are talking about this value element 4. The one thing that arises in your mind, why to so go from the backward side, and why to sort the elements on the basis of vector pairs? As I've already said that for every element, you can see I'm talking about the element 4. The next greater element is to the left of is 5, and next greater element to the right of is 8. You can see both the elements are greater than my current element. It means that you need to process the elements from the value, that is from the maximum value, and it goes up to the minimum value, right? That is, you need to process from the backside of the array, and the array must be sorted in increasing order. Okay, so if you store the elements in a set, it has the value 0 3 4 6 7, and if you claim that 4 is the maximum element, then how you can increment your answer? What is the backward of I and what is the forward of I? You can easily see if you try to find out the next greater element of this 4. Note that the term next greater element of this 4. What is the index of 4? 4. Okay, so let us try to fetch the index of 4. You can easily see the index of 4 is coming out to be 4. Okay, now one thing that should be kept in your mind, that all the elements in the set whose indices are present are all that is all the elements have the value greater than or equal to my current value. Okay, so if I will try to fetch the index equal to 4, the next index is going to correspond the index of the next greater element of the value 4, right? And also the next greater element to the left of it, that is the index being smaller than 4, this one is going to be this one. Okay, and if you need to find the backward of I, backward of I is the difference of this, and forward of I is the difference of this. 6 4 is coming out to be 2, and 4 3 is coming out to be 1. This is the backward of I, and this is the forward of I, and you need to do the things in a backside manner, that is when you sort the array and process the elements from the backside. So this is the backward of I, and this is the forward of I, and if you product this one, you get the number of subarrays for the current element. Okay, let's cross check it out if the values that I've gotten is correct or not. So if you look over this one, like if you look over this 4, what is the backward of I? You can see the next greater element is 5, so you can choose the L minimum as the index equal to 4. So the only one element is going to be corresponded in the backward of I. And what is the forward of I? What is the R max? You can see R max is coming out to be this index equal to 5. So my answer would be like only two elements. You can include this 4, or you can include this 3. You cannot include this 8. 8 is present at index equal to 6. So I'm not going to include this 8. I can include these only two elements. So my forward of I is coming out to be 2. And if you cross check this value, you can see yes, it is coming out to be correct. So it signifies that we can process the elements from the backside of the array. Okay, so let's move further to the coding part. Okay, so where is that? Okay, I've already submitted some bullets. Why not to show that one? Okay, I've also tried to do this problem with the help of next greater element using stack and with the help of stack, but I am getting a frequent wrong answer. Like I don't know, the test cases were like this one, and there is some flaw in this one. I am not able to figure it out. So I've done using binary search. Okay, so moving further to the explanation of this, I've taken answer as 0 and as nums dot size. I've taken a vector pair sort on the basis of nums of I and I, and you can see that I've pushed back the elements as nums of I comma I, index I, and the value corresponding to that, and sorted in non-decreasing order. And now I'm processing from the back side, right? I equal to n minus 1, I greater than equal to 0, I minus minus. You can see I have pushed back the minus 1 and an element n into my index. Index is basically the set that I'm going to maintain so that I can find the next greater element index, and next small, that is the next greater element to the right of my current element index, and the next greater element to the left of my current element's index with the help of this index set by taking the lower bound or upper bound, you can say. What I have done is start processing from backside of the array of vector pairs. Okay, so index, first I've inserted the indexes. Note that the term that I am going to use over here, like I am working on the index, right? Each time. Why to work on the index? Because I need to find the number of elements. Okay, so if my range current value, that is vi dot first, that is the nums of I value, is not in the given range, just move further. No need to find the number of subarrays corresponding to this maximum element. Otherwise, find the next pointer, which is basically the index of the next greater element to the right of my current element, and similarly the previous one with the help of this find one, using set dot find, and just decrement one position backward. Okay, and what is the number of elements to the left of it by using this is actually the backward, and it is actually the vi dot second minus the previous index value. Okay, and this is the forward, and total number of subarrays possible would be like backward into forward, considering current element as the maximum element, right? And finally return the answer. So this is basically the accepted code. So if you have any doubts, do let me know in the comment section of the video, and do not forget to like this video, share this video, and to subscribe to our YouTube channel for latest updates. Thank you for watching this video.